Good afternoon, everyone, and thank you very much for such a great opportunity. I'm glad to present you our robot today. All right, my name is Seiya Shimizu. I'm a software engineer and the project manager of the GITAI LAO Technological Demonstration Mission at GITAI. GITAI is a Los Angeles-based startup company focusing on providing robotic solutions for space applications. Our mission statement is to provide us affordable and safe means of labor in space. There is a growing demand of space-related services. NASA kicked off their commercial space station programs, and multiple space agencies had warned of potential risks associated with space debris. And on-orbit services had called attraction of both government and private sectors. And of course, the Moon and Mars surface become realistic destinations of commercial, not only for commercial, but development. However, the current workforce is insufficient to meet these demands. The primary challenge in space development is the cost of transporting humans into space. Thanks to new space companies like SpaceX and Blue Origin, the cost for the space transportation has reduced significantly. However, the expenses related to human labor remains high due to the value of human life. Ensuring astronaut safety requires substantial investments in training, equipment, and procedure. The cost per man-hour for an astronaut is $130,000 US dollars, presenting a significant barrier for achieving sustainable commercial space development. Our goal at GITAI is to address this issue and help revolutionize the industry by providing cost-effective and safe robotic solutions. GITAI is currently focusing on 3 key domains: space station support, on-orbit servicing, and lunar city construction. In 2021, we launched one of our prototype robots, the S1, to the International Space Station to support the IVA, the intravehicular activities. And this year, we plan to launch another robot to the ISS again, the code S2. That robot is designed for on-orbit servicing and in-space manufacturing assembly. In addition to our space-based robots, GITAI has developed multiple rovers, dexterous manipulators, and robotic arms for ground experiments. These robots demonstrate our capability to construct large-scale objects on lunar surface. GITAI has invested in maturation of technology to support both private companies and NASA's ambition to establish a permanent presence on a lunar surface. Today, I'd like to share with you a glimpse of our investments in cutting-edge robotics technology. I will provide an overview of the robots we have developed and accompany each with a video demonstration. In each domain, we have developed multiple robots, all featuring our in-house developed components. This showcase will offer a deeper understanding of our commitment to innovation and the capability of our robotic solutions. So let's start by taking a look at our first in-space technology demonstration, the S1 intravehicular support robot.
Since Shane Interact back with you, glad to see you.
The S1 was deployed
just
to the International Space Station in 2021, following its successful completion of NASA's safety reviews. Full compliance with NASA's ISS safety standards the S1 showcased its exceptional dexterity in microgravity environments. Once the robot arrives at the ISS, the crew installed it at the designated experimental site. The demonstration involves various astronaut IVA tasks, including assembly, disassembly, and cable management and switch operations. The task you see now is involves assembling panel mount frames and the panels like a solar arrays. Under a ground computer, the operator can view the robot and its environment as a 3D model with camera images and depth information overlaid onto the 3D model. By observing these visuals, a ground operator can confirm that the robot is functioning as expected. The S1 tasks also encompass switch operations. The robot can push buttons, toggle pins, and rotate knobs and insert cables. With its onboard computer vision software, the S1 can perform these tasks autonomously. However, if needed, a ground operator can control this robot using a teleoperation interface. This versatility ensures that the S1 can smoothly integrate into currently existing space station procedure and processes.
Insane.
Okay. Another important aspect of the space station sport is extravehicular activities, EVA, which involves tasks such as capturing and berthing the visiting vehicles, as well as station inspection and maintenance. To provide solutions for these tasks, we developed a 10-meter long inchworm arm. The term inchworm refers to the robot's ability to move around like an inchworm. The robot features identical end effectors on both ends, which allows it to move by capturing fixture points. Last December and January, we conducted neutral buoyancy experiments with this inchworm arm. Although the video is not publicly available yet, we will posting it on our company's YouTube channel soon. In the experiment, we placed multiple fixture points on the walls and floor of an 8-meter pool, and the robot worked on these fixture points. This test demonstrated our ability to build and control a 10-meter class robotic arm. Since this was a rapid prototyping project with 3 months for hardware and software development, we utilized the same core components we already had in our arsenal. Thanks to the flexible capabilities of our hardware and software stack, we were able to successfully complete the experiment with minimal new development. For on-orbit servicing, we have a plan to launch another robot, the S2, to the ISS this year. The S2 is equipped with 2 robotic arms and redundant onboard computers. It will be stationed at an external experiment site on the ISS for 6 months, during which it will demonstrate its capability to perform larger scale in-space assembly and unit replacement tasks. Currently, we have completed 70% of the ISS safety review processes for the S2. The final review is scheduled for this coming June, and upon successful completion, the S2 will be ready for deployment to the ISS. Before launching the S2, we did and we will conduct multiple environmental tests, including thermal braking tests, vibration tests, and radiation tests. One of the most significant tests was the space chamber test we carried out a year ago. We placed our entire robot into the JAXA's 8-meter space chamber and ran a full sequence of task operations. The robot in the video is a previous generation prototype, and while its detailed design differs from the flight model, the overall experiment concept remains largely the same. Okay. In the control room, we had 3 software engineers as robot operators, along with an operations supervisor. The operating consoles for the robot consisted of 6 laptops, 6 normal laptops, and multiple large display monitors. Similar to the S1 experiment, the operator observed the robot and the environment's 3D models to ensure that the robot's motion was as expected. Unlike the S1, the S2 does not have depth sensors, but instead features more telemetry data for each robot joint and 2 high-definition cameras on each hand. During this experiment, actually the robot dropped the panel once. However, the robot with our operator successfully picked up the panel and continued the rest of the experiment. I think now this is the actual scene of the failure. Our yes, the failure occurs during the test procedure, but the research and development approach is to build a lot, test a lot, and learn a lot. We continually refine our software and hardware through the real-world experiments. This R&D strategy has allowed us to roll out new robots every 6 months and send robots to the space every 2 years. Through these environmental tests and the end-to-end experiments, we have increased technological readiness level of our products. In addition to robotic arms, we also develop rovers. Our rover R1 is equipped with 4 independently moving wheels, 2 dexterous robot arms, and a sensor head. We tested the rover's mobility and task capabilities at the Lunar Environmental Simulation Facility. The mobile platform software was designed and implemented in-house, sharing a significant portion of the code base with the robot arms software. The platform demonstrated successful motion in the sample, and besides its mobility, the rover's teleoperated robot arms can handle multiple objects in sandy environments. The operator can view the rover's perspective through a head-mounted display. By using a haptic interface, the operator can control 2 robot arms as if they were their own, providing a seamless and intuitive user experience. This teleoperation interface is also an in-house developed software and it is an advanced version of the teleoperation software we demonstrated on the space station in the S1 demonstration. Our most recent field experiment involved large-scale construction in a desert environment. The group photo displayed here shows GITAI's current robotic fleet, and the video of this experiment will soon be available on YouTube shortly. For lunar city construction, the multi-robot cooperation is essential to complete large-scale projects. To demonstrate how our robots can coordinate to building our lunar city, we developed 2 rovers, 4 robot arms, and initiated field experiments showcasing their collaborative capabilities in a relevant environment. The robot arms can move rovers and buildings and providing flexible capabilities for construction, inspection, and maintenance of buildings on the Moon or Mars surface. Our robot control software supports multiple robot configurations, enabling us to operate several robots together. So far, we have completed three desert experiments and plan to conduct more this year. We look forward to sharing our additional achievement with you later this year. The robot I've shown you so far has been developed primarily for tech demonstrations. But does this mean that GITAI is just a prototyping company? The answer is clearly no. We already have customers. Leveraging our technology, we built a robotic arm for Toyota's lunar rover, and Toyota is not our only client. While I cannot disclose specific details, we have received purchase orders from both commercial companies and government sectors, and we continue to expand our reach and influence. In this presentation, I've shown several robots that we've developed. I want to emphasize that we created all of these robots in-house. GITAI is committed to vertical integration, which means that we design, build, implement, and test our hardware and software by ourselves. Our software development process is closely intertwined with hardware development. Software engineers at GITAI work hand in hand with mechanical and electrical engineers to enhance our robot capabilities. Our software portfolio has distinct strengths in both the application layer and base framework. At the application layer, we have developed expertise in computer vision, motion planning, and teleoperations. In the base framework, we focus on real-time control and diagnostic framework. Now let's dive into the S1's control system. S1, as I mentioned, it was launched to the ISS not last year, 2021, and completed its technological demonstration. As our prototype for intravehicular support robots, S1 possesses both teleoperation and autonomous control capabilities. The robot transmits vision, depth data, and telemetry to the ground computer. The ground operator can control the robot using a haptic controller or let the ground computer calculate the robot's next motion based on the task sequence status. The motion planner on the ground computer ensures that generated motion does not collide with any nearby object before sending the command to the robot. Once the robot in the space receives the command, its real-time controller spreads commands to actuate the robot's joints. As the robot moves, the real-time controller monitors joint and four-stroke sensor telemetry to ensure the robot is moving as expected. This control system enables efficient and safe operation of the S1 robot in the ISS environment. And now for the S2. Unlike S1, S2 is designed for autonomous operation under limited network availability, such as narrowband communication on GEO satellites or loss of signal period on space stations. As a result, S2's motion planner is implemented on its onboard computer. The motion for each task step is generated on orbit and transmitted to the ground. The ground operator and the ground computer are then responsible for approving the planned motion. Once authorized, the motion is sent back to the robot in space, where the real-time controller distributes the actuation command to motor drivers in each joint. During the robot's movement, the real-time controller monitors joint angles, voltage, current, as well as force and torque of the end effector. If any anomalies are detected, the controller immediately shuts down the robots to prevent unintended motion. This system ensures safe and reliable operation of S2 even under challenging communication conditions. The operation of the end effector is a crucial aspect of robot operation too. At GITAI, we've developed a comprehensive software package for perception, planning, and verification. This package can be applied to multiple types of interfaces that GITAI has designed. Our visual target, a common fiducial, is small and versatile, making it suitable for a range of applications such as cables, on-orbit replaceable units, and tools. The gripper also functions as a tool changer, allowing it for different types of tools to be attached as needed for specific tasks. These tools are controlled by the same software package, ensuring the seamless integration and operation across, across various components of GITAI's robotic systems. This unified approach enhances the overall efficiency and adaptability of our robots, allowing them to perform a wide range of tasks in various environments. Now you might be wondering how our software contributes to mission assurance and safety. At GITAI, our basic design philosophy is to ensure safety through hardware layers, while software focuses on enhancing the robot capability and performance. By isolating safety-critical features from the software, we can develop more rapidly and flexibly. However, this doesn't mean that our software is designed and operates without any consideration on safety. Our software includes a built-in collision check that prevents motion planner from generating trajectories that could potentially collide with nearby objects. Additionally, the controller monitors 6 key data points: trajectory, encoder discrepancy, end effector force, violation of keep in or keep out volume, and current and network health. If any anomalies of these key data points are detected, the real-time controller will shut down the robot to prevent accidents and ensure the overall safety of the system. Okay. As mentioned earlier, the GITAI software engineers work closely with hardware engineers. Log data from various environmental tests are gathered and stored using the same data analysis platform as the flight software. Utilizing the same infrastructure for more frequent tests proves beneficial, as it allows us to improve our diagnostic frameworks and keep it up to date. This close collaboration between software and hardware engineers helps ensure that our robots are equipped with the latest technology and perform at their highest potential. Then naturally, our software engineers are also involved in the external environmental tests too. To wrap up, I'd like to invite you to visit our office in Torrance, Torrance, California. Just a short 20 minutes drive from Los Angeles International Airport, or about an hour from here, Caltech, Pasadena. We have all of our robots on display here, and we'd be thrilled to have you stop by and see them in action. Don't hesitate to drop by and check out the real robot working. By the time you visit, we will likely have more robots than the ones I introduced today. I'm looking forward to hosting you at our office soon. All right, thank you very much.